Hello and welcome to yet another video. Today we'll be talking about solubility product. I know it's an overwhelming topic. My 2 subscribers seem to indicate that I couldn't possibly be blowing up more on YouTube. Keep cashing those monetized video checks. It's going to be pretty crazy. Next time you guys see me, I'll be rolling up in a Tesla. So the last part of chapter 17 is what's known as solubility product. And solubility product, you may recall way back when we were actually meeting together, we're talking about the last of the K values for equilibrium, KSP, where the SP stands for solubility product. You may recall that I mentioned it was a double entendre, meaning it has 2 meanings. The meanings are that the products of something soluble are the ions that you get at the end of it, and it's also those concentrations of those ions multiplied together. So it's a mathematical product and the chemical product of a reaction. I don't know if it was intended to be that way, but it certainly works out to be that way. So what we're really talking about is measuring the solubility of things that we would normally have described earlier in the year as not soluble. So measuring the solubility of ionic compounds that we might label as insoluble or largely insoluble. So things that don't appear to dissolve very much in water, but actually do in fact dissolve a little bit. So, for example, let's imagine that we have something like calcium carbonate. Limestone, essentially, or one of the big components of limestone, or marble. If I were to put that in water, you think if you take a chunk of marble and drop it in water, nothing appears to happen. I mean, the chunk of marble would go in, and it would appear as though you could leave it there for a century or more, and nothing would happen. I mean, witness all the marble statues, marble buildings all around the world. They've been there for hundreds and thousands of years with no damage other than that of acid rain, which we'll talk a little bit more about. But certainly nothing appears to happen, and there appears again to be no dissolving. But if you were to very carefully measure the amount of calcium carbonate that you put in, and then you take it out and dry it very carefully, you would see, in fact, that a very little bit of it does dissolve. And you could obviously confirm that. You might think, well, maybe a little bit of it chipped off or whatever. You could remove it, dry it, weigh it, and then also examine the watery solution for the presence of ions, and you would indeed find some calcium and carbonate ions. Not very many, but you'd find a few. So KSP sort of seeks to describe, what if I put a speck, a tiny amount of calcium carbonate into water, and it dissolves, and then I add another speck and it dissolves, and I add another speck and it dissolves, and maybe the 4th speck that I add, it stops dissolving. Well, then I've sort of discovered, oh, like, if this is how much calcium carbonate actually dissolves, I've discovered its saturation, its maximum solubility under those conditions. And that's what KSP seeks to describe. So KSP tells us about saturated solutions. So the idea is how much, what is the most of this substance that we could dissolve. So let's look a little bit more at the math of this. I know it's been a while since we've done math, but we are going to do a little bit here and there throughout the year. Let's say that we have calcium carbonate. We drop that chunk of solid in. We give it enough time for a little bit of it to dissolve, and we have a way of detecting that there are small amounts of these ions present. They certainly make specific ion detectors. We could also measure things like electrical conductivity, pH changes, etc., to kind of see what's going on. We know that calcium doesn't really impact pH in any great way because it doesn't stick to OH-, but carbonate does indeed stick to H+. So the pH would get a little bit basic as we did this and that sort of thing. So there are various ways that you could measure how much of this actually dissolved. And it's not very much, as we'll discover. And so people come up with what are estimates for these things. So the KSP expression would simply be that KSP equals the molarity of Ca2+ times the molarity of CO3 2-. And that, you'll note, there's no denominator here because the calcium carbonate is a solid. And because it's a solid, we're going to leave it out. And so it's not included as part of this whole thing. So again, when we talk about solubility product, it's just a product. There's no division that goes on here. At 25 Celsius, standard temperature for all sorts of things, the KSP for calcium carbonate is 3.3 times 10 to the negative ninth. That obviously is a reaction that heavily favors the solid. So again, that is in line with what we experience. We put marble in water, or marble buildings and statues stand outside, and they do not dissolve at the first rain. So we know that the solid is certainly very heavily favored and can certainly be heavily favored for hundreds and thousands of years without dissolving. If we wanted to find out, what is the solubility of calcium carbonate, in other words, how much or how many, and we can describe this in two ways as we'll learn, how many moles of CaCO3 can be dissolved in a liter of solution. So what we're really trying to find out is, how much calcium carbonate could I add to a liter of water roughly until it stops dissolving. So how much CaCO3 will dissolve before it stops dissolving. And that's a pretty easy math problem to set up, simply because we know that that's 3.3 times 10 to the negative ninth, and that equals the molarity of Ca2 plus times the molarity of CO3 2 minus. Well, in a solution of just calcium carbonate, these two things are going to be equal to one another, because every time we get one of the other. And so they should actually be identical, which means 3.3 times 10 to the negative ninth equals x squared. X will equal the square root of that. That would be the square root of 33 times 10 to the negative 10th. And that is probably somewhere in the neighborhood of like 5.8 times 10 to the negative fifth molar. Don't leave comments about how it's 5.7 or 5.9. I don't have a calculator right now any more than you probably do right by you, so I'm doing the best I can. So that would be the value of Ca2 plus or CO3 2 minus, but the beautiful thing about this is there's a 1 calcium carbonate to 1 of those ions ratio, so it actually is the same value. Let's clean up that handwriting a little bit. It is actually the exact same value for calcium carbonate. In other words, you can dissolve about 0.000058 moles of calcium carbonate in 1 liter before it stops dissolving. So very, very little. Given that the molar mass of calcium carbonate is around 100 grams per mole, we're talking then you can dissolve about 0.0058 grams in 1 liter. So about 6 milligrams of calcium carbonate per liter. So a very, very low solubility. Very little of it would dissolve in water. And that's our experience. I mean, we know that things that are made of marble, we know that limestone, where much of our school sits, the foundation of the ground of where we are is a lot of limestone. Like, it certainly doesn't turn into a gigantic lake every time it rains. And then we just hope that it dries out enough to precipitate back the solidity of our state. So it doesn't really work like that. Now, there are a couple of things that we're going to get to as we go through some of these problems. There's sort of 3 extensions, and I at least want to mention those today, and then we'll kind of get into how this works more specifically in the next video. But the 3 extensions to this idea, all of which I think are quite important, and we'll sort of get into those a little bit, and we'll start to do some math again because it has been a while. The first one is simply the common ion effect. So what if we have what if we have something where a solution isn't just water, but what if a solution contains one of the ions that we're talking about? So in other words, instead of pure water, what if we tried to dissolve the CaCO3 solid into a solution of calcium chloride? So one that already contained calcium 2+ ions. How would that affect things? And we'll obviously apply some ideas of Le Chatelier's principle here, and then we'll do some math with it as well. But if there's already calcium 2+ in there, that's obviously going to push the reaction back towards the solid side, and we'd find that it dissolves even less. You could also flip this on its end a little bit and say, well, what if it's sort of the uncommon ion effect, and what if I have a solution that actually removes one of the ions as it's made? So what if I have something that can actually like pull calcium or carbonate out of solution? That'll make it even more soluble. And that's the effect, as we'll talk about, of something like acid rain. The acid adds the H+ to water. That actually knocks out carbonate and makes the solution actually more soluble, which is why a lot of marble buildings and statues, certainly in Europe, had to be moved inside during the Industrial Revolution and since, because there were so many non-metal oxide gases being produced in all the burning, all the combustion, that the rain was becoming quite acidified, and that rain, as it fell on statues that had stood for thousands of years unharmed, was dissolving those statues, and so they were moved inside as they began to be rather heavily damaged. The second thing that we'll talk a little bit about is this idea that you can use these values to predict whether something is going to form or precipitate or not. So if I have two different solutions, so if solutions with, let's say, calcium 2+ and carbonate are mixed together, will we get a precipitate? And that's a fairly easy calculation in this particular circumstance, because you would just multiply the molarities of calcium and carbonate together according to the KSP expression, and then just do a little Q versus K, and if it's higher or lower than K, that tells you whether there would be a precipitate or not. And we'll do an example problem of that in the next video as well. And then the third thing is, what about non-1-to-1 ratios? So what if I have something like CaF2, and that relationship isn't all nice and easy and 1-to-1-ish, because we've got the two F minuses in there. And that means that KSP equals calcium 2+, but it also equals F- squared. And again, the effects there, I think, usually trip people up, that the idea of F-, it has two effects, that you get twice as many ions, and then that has an exponential effect on the rate of reaction and the number of collisions. And so you end up having to both double it and square it. And that causes a slightly different mathematical approach than you might at first glance think. But that's going to be coming up in the next video. No reason to worry about it too much today. This is just an introduction to KSP. So let that sink in a little bit, and then if you can hold off, and I know the excitement must be high, but if you can hold off, we'll do the next video tomorrow and we'll get into all this stuff. But if you must go ahead, the video, I'm sure, will be waiting for you on the massively popular YouTube channel. All right, talk to you later.